Ok. Bene, allora, benvenute e benvenuti a tutti. I apologize to our guest, Professor Rajagopal, because we will start with this welcome introduction in Italian, but we will switch to English immediately after, ok? Bene, allora, grazie a tutti quelli che sono presenti, anche chi seguirà live su YouTube o registrato il contenuto rimarrà. From MOOCs to Magic è un bellissimo titolo, è un argomento di grandissimo interesse. Come Ateneo di Padova, noi siamo leggermente, abbiamo un Teaching for Learning, un Digital Center che lavora molto bene, siamo all'avanguardia in Italia e stiamo lavorando per continuare a migliorare e, indirizzarci a consentire a tutti i nostri colleghi, corsi di studio che vorranno spingersi verso maggiori modalità online, quelle con le quali siamo venuti in maniera, violenta a contatto durante il periodo del Covid e vogliono muoversi in questa direzione. Muoversi in questa direzione cosa vuol dire a livello, che fa carico al mio prorettorato? Vuol dire modificando la modalità del proprio corso di studio, quindi o sposando il 10%, che però è un vincolo molto stretto in un corso convenzionale, di possibilità di erogare modalità online, didattiche in modalità online, oppure modificando la modalità a quelle che vengono definite modalità mista e modalità prevalentemente online, che sono le tre consentite. Mista vuol dire che si può arrivare fino ai 2/3 di didattica erogata in maniera online e prevalentemente oltre 2/3 di didattica. Per fare questo è una grossa sfida, è una sfida tecnologica, è una sfida di aggiornamento dei docenti. Bisogna staccare il ricordo che si ha dal Covid, non è fare lezione in Zoom mettendo semplicemente, sostituendo la lavagna o il proiettore con lo schermo dello studente, è rimmaginare i propri corsi di studio, quindi è indubbiamente indirizzarci in un nuovo mondo. Io l'impressione che ho è un po' come il nostro Ateneo una decina d'anni fa si è avvicinato all'internazionalizzazione, ad aumentare la propria presenza nei corsi in inglese. Chi ha come me molti anni di esperienza alle spalle ci ricorda che avevamo fatto vari tentativi, singoli insegnamenti nei corsi di studio in italiano, avevamo difficoltà a attrarre studenti Erasmus e tutto, e un po' alla volta si è partiti, si è iniziati, e adesso 1/4 della nostra offerta è di corsi di studio integralmente in lingua inglese. Adesso nessun collega, penso, si volta indietro se gli viene detto prossimo anno può insegnare un insegnamento nel corso magistrale che è in inglese, lo farà in inglese. È accettato. Quindi noi siamo, per quello che riguarda le modalità dei corsi di studio non convenzionali, come vengono detti in termini, burocratici, siamo assolutamente agli inizi. Il 2% della nostra offerta di quest'anno è non convenzionale. Su 203 corsi di studio abbiamo 4 corsi di studio che non sono convenzionali. Però qualcosa si muove. Il 60% dei corsi di nuova istituzione che partiranno l'anno prossimo sono in modalità mista. E questo ci porterà tra un anno ad avere raddoppiato la percentuale di corsi non convenzionali. Quindi c'è un movimento, c'è un'esigenza. Stiamo preparando delle linee guida per aiutare chi si vuole inserire in questa, non la chiamo rivoluzione, in questa possibile evoluzione. Mi raccomando, è un'opportunità che l'Ateneo dà ai corsi di studio. È un'opportunità da valutare e da decidere e, secondo me, arricchisce il corso di studio. Noi stiamo pensandolo per corsi di studio online, per gli insegnamenti blended, ma si può trasportare tutto anche nella didattica fatta in aula, standard con gli studenti in presenza. Quindi è qualcosa che dobbiamo far, passare, renderlo un valore condiviso, e ringrazio gli ospiti che saranno qui oggi. Adesso passerò la parola a Marina De Rossi che farà un'introduzione più sul nostro, la nostra attività già che è fatta da molti anni, il Teaching for Learning, su questo tipo di tematiche, e poi sentiremo il collega che, gli dicevo prima, ci porterà con mano probabilmente a vedere un po' il futuro, perché sono nettamente più avanti di noi e quindi ci potrà far vedere leggermente un po', anticiparci quello che possiamo aspettarci tra qui a qualche anno di poter vedere anche nel nostro Ateneo. Quindi ringrazio tutti. sarò come voi molto attento e ascolterò con molto interesse tutto quanto verrà detto dal professor Rajagopal prima e poi nella tavola rotonda che seguirà. Grazie ancora.
Bene, ringrazio anch'io per questa occasione molto importante che sottolinea il lavoro che si sta facendo e l'interesse che si sta muovendo intorno al tema dell'innovazione, della didattica, naturalmente tenendo sempre conto di mantenere degli standard di qualità elevati. Noi come azione del progetto Teaching for Learning, che è un progetto ormai consolidato nel tempo, partito nel 2016, naturalmente fungiamo, diciamo, da supporto e da stimolo per questi processi di cambiamento trasformativi che ci ha appena raccontato il nostro prorettore alla didattica. Utilizzare MOOC, utilizzare una didattica blended, trasformare la modalità di erogazione sono processi complessi che richiedono tempi lunghi, una maturazione e soprattutto una formazione che porti alla consapevolezza dell'importanza del considerare la didattica non solo una trasmissione di contenuti, ma naturalmente un processo continuo di dialogo rispetto a quella che è la trasposizione dei contenuti attraverso approcci metodologici e naturalmente l'integrazione del digitale. Quindi questo supporto che noi diamo attraverso il progetto e attraverso anche molte persone, una comunità attiva intorno a questi obiettivi, che è la comunità dei nostri change agent, che sono docenti che nel corso del tempo si sono formati e sono diventati dei veri e propri agenti di cambiamento all'interno dei loro dipartimenti e come supporto e appunto aiuto anche per chi vuole cimentarsi in un'innovazione. E come dicevo, appunto, noi fungiamo da supporto, anche da stimolo attraverso quella che è una grande azione che l'Ateneo fa, cioè il finanziamento annuale per i progetti di miglioramento della didattica a cui possono aderire volontariamente i dipartimenti e sono proprio lo stimolo per cambiare, per ritrovarsi insieme e provare a progettare in maniera differente. Per quanto riguarda proprio l'innovazione digitale, in particolare i MOOC, e il cominciare a lavorare, a produrre dei MOOC, che è già uno stato avanzato nel nostro Ateneo, c'è proprio una linea specifica nel nostro progetto che finanzia e aiuta a sostenere questa azione. Quindi tutto questo nel tempo ha costruito, come si diceva, una maggior coscienza anche nell'opportunità di scelta, perché naturalmente sono scelte che liberamente i docenti possono fare, ma che poi condivise con gli studenti possono effettivamente portare a un modo nuovo di intendere la cultura del digitale in maniera responsabile, in maniera qualificante e naturalmente sempre critica rispetto alla complessità dell'integrazione di nuovi strumenti. Quindi grazie oggi per questa iniziativa, anch'io ascolterò con attenzione e appunto buon lavoro a tutti. Grazie.
Grazie, io passo invece all'inglese. Welcome to everybody. I'm here to welcome you in the name of the Galilean School, who's been the first organizer of this event. And then I thank, of course, the university and especially the Vice Rector for teaching, who helped us in organizing this event. And you know, the Galilean School is the excellent school of this university. And of course, we are committed to having excellent students, but to have excellent students, you need, of course, an excellent teaching, excellent teachers. And therefore, we are open and interested in understanding all possible innovations in teaching. And this is the idea of this event. I will now introduce the speaker, Professor Rajagopal. Professor Rajagopal is currently William Burden Professor of Physics at the Massachusetts Institute of Technology. Before MIT, he received his undergraduate degree at the Queen's University in Kingston, Canada, then the PhD from Princeton University. Then he has been a junior fellow at Harvard University, Fairchild Fellow at Caltech, and then he landed at MIT. Professor Rajagopal is an excellent scientist. He's been giving very important contributions in physics, especially in the field of understanding the strong interaction, but not only. But he's here today also because he's an excellent teacher, and he's been receiving several awards for both teaching and advising. And especially because he's been the MIT's Dean for Digital Learning from 2017 to 2021. So we are very happy that he's been gladly accepting our invitation, and I will just leave the stage then to Professor Rajagopal. Welcome and thank you.
So you want me to put this down? So thank you very much. Can you get my slides on the... So thank you very much, Gianguido, for the invitation. It's a privilege to visit Padova, the Scuola Galileana de Studi Superiori, and also to meet earlier today some of the leaders in teaching and learning here. Okay, so can we get them on this also? And it's a distinct pleasure to be speaking in this historic room. It's really hard to beat. I don't think there's. I've given many lectures in my life, but never in a room quite like this one. So I thank you for that privilege also. So in the title of my talk, From MOOCs to Magic, sometimes one has to explain what a MOOC is. I don't think that's necessary here. But what do I mean by magic? The use of the word magic in my title comes because, at least at MIT, we have talked, as long as I've been at MIT, for decades we've used the phrase, the magic of MIT, the magic of MIT. And I will say we didn't really think about what we meant. The magic of MIT is a phrase that we've used forever. You perhaps, magic of Padova doesn't sound as good as magic of MIT because of the alliteration in the two M's. I was talking with Francesco earlier, maybe it's the perfection of Padova, I don't know. You have to come up with, I'm not sure what your phrase like that is, but for decades we used a phrase like that without thinking about what we actually meant, and then in spring of 2020 when COVID came, we lost it. In spring of 2020, at MIT, as everywhere, everyone had to go home. And that prompted a lot of us to ask ourselves, what actually did we mean by the magic of MIT? What is it that we had before that was magic, that we had all of a sudden lost? What is the magic, and how do we and our students create it together? So for me, the magic is the point of an on-campus education. It's the answer to the question of why do we come together on a campus to learn and to teach? In the time of Galileo, of course, you had to come to campus for the content of the education. You had no access to the knowledge if you didn't come here. That's not true today, and that hasn't been true for many decades. So I teach Maxwell's equations. If you want to learn the content of Maxwell's equations, you don't have to come to MIT or to Padova. You can find it in the library or online, and that's been possible for decades. So what's the magic? What's the reason we come together on a campus? It originates from the kind of unscripted engagement between people, between humans, between students and students, between students and teachers. There are many kinds of random, unscripted engagements that I'm thinking of. If you think back to your time as a student, the office hours that you remember, the conversation you had with a professor in their office where all of a sudden something clicked. And from the faculty side, the conversation you have with a student where you can see in their eyes that they just got something for the first time. But it's learning to wrestle with a difficult problem from an expert, learning a new way of looking at problem solving. It's working late at night with your friends, 2 in the morning, wherever you are at 2 in the morning, doing your math homework or your philosophy homework. It's the project classes where you built that robot and it was the day that the robot actually worked for the first time. It's the lab classes. It's the time in your research lab when something clicked for the first time. Maybe it's the debate that you had with a professor where you were going at it hammer and tongs, disagreeing about something, or the debate you had with one of your best friends who you've been friends with for the rest of your life. All of these kinds of things added up over thousands of students, tens of thousands of students, thousands of faculty. All these engagements are what together are the magic. And we lost it all for about a year, starting in the spring of 2020. And when we came back, we had been forced to do things in new ways while we were remote. And some of the things we learned how to do during that remote year are keepers. They're things that we've continued with. And in fact, in late 21 and into 2022, I co-chaired an MIT-wide committee on leveraging best practices from remote teaching for on-campus education. And we were asked basically to listen to the experience of educators across MIT. Nobody ever wants to repeat 2020. It was a horrible experience. But we actually did learn how to do some things then that we're still using today. And we wrote a report giving dozens of examples of things that we had learned how to do that we were continuing doing, even now that we're back together, to make the magic better. And the themes in what we heard from educators across MIT, a lot of them had to do with building, increasing well-being, building belonging, strengthening community, because those of us who are faculty, it's normal in normal times to focus on the content of what we teach. But all of a sudden in 2020, when we lost that community, we spent a lot of effort trying to build and maintain community, and that has carried forward in good ways. I will say in many ways, I think the best thing about that bad experience was that we were forced to think from first principles about pedagogy. Not just what are we teaching, but how are we teaching, and what is it we want our students to learn? How can we best help them to learn? And we were forced to think that way because we had to go back to first principles because we were doing things in a way that none of us knew how to do. And the thinking about pedagogy that all of us did in that year, I think, is bearing fruit today. We developed new ways of enhancing engagement, of enriching and augmenting the learning environment. There's a report that this committee wrote. It's intended for internal purposes. The idea of this report is to share knowledge from one sector of MIT with other sectors of MIT, but if any of you want it, it's publicly available, although not written for a world audience. It may still be of interest. I will just say a brief word about what I mean by increasing authenticity. I'll come back to this at the end. So when I said enriching and augmenting the learning environment, one aspect of that is increasing authenticity. Let me give you an example. Suppose that I'm teaching a class in which I want to teach my students about dark matter, one of the great unanswered questions in physics. And I happen to know that one of the world experts is Professor De Rossi from the University of Padova. How can I give my students at MIT the authentic experience of hearing from Professor De Rossi and asking questions, having an engagement with Professor De Rossi? In the old days, that would have required asking him to fly to Boston, and we do. Here I am in Padova, and he's been in Boston. But you wouldn't do that just for a 30-minute engagement with your class. We don't fly each other fly a colleague from halfway around the world just for 30 minutes in the classroom. And now we don't need to, because all of us in 2020 learned how to use Zoom. So I can increase the authenticity of the learning experience of my students at MIT in a relatively straightforward and really almost trivial way by bringing in experts who are world experts on whatever it is I want them to learn about. I can actually bring them together by Zoom. So that's a pretty trivial example. I'll give a much better example at the end of the lecture. What I want to spend most of the time on is these two phrases: enhancing engagement and blended learning as a way of enhancing engagement. This is something that we had been doing at MIT for 20 years, but it was really, I think, supercharged the impetus for thinking about blended learning and doing so in a way that enhances engagement, creates more magic. This was really driven home in 2020, and as I'll try to explain using examples from physics at MIT, we're now much better at it than we were in 2019, let's say. So what do I mean by blended learning? I mean using digital tools to enhance the in-classroom learning experience. The reason that our students come together in a classroom should be to make magic. They don't need to come to the classroom to have access to content. The reason for being together in the classroom has to be about the engagement that happens in the classroom. And if you want to open up time and space in the classroom for engagement, interaction, active learning, I'll show you examples, then how do you deliver the content? Well, you can deliver the content to your students outside the classroom using online tools, and again, I'll show you examples. And once you're doing that, you can share the content of the class with the whole world via a MOOC. MIT Physics has been a leader in doing all of this in active learning for the past 20 years. This phrase, blended learning, is a nice phrase because it gives you a sense that there must be lots of different ways of doing it. There's not just one mode for blended learning. And in fact, what kind of engagement, what kind of interaction, what's the magic you want to try to create in a particular classroom depends a lot on the subject matter and the level of the class, and I'm going to give multiple examples. And once you've created the learning materials that your students are using on their own time in their dorm room before they come to your class or after they come to your class, you can share those materials with anyone via a MOOC, and the MOOC doesn't include the magic. So what you share via the MOOC is drawn from the classroom experience, drawn from the experience of your students at your university in Padova or at MIT, but it doesn't include the magic. To experience the magic of being in the classroom and with a group of peers and with instructors, you have to be together in the same classroom, in the same space. So sometimes people ask, why do professors make MOOCs? And I will give the answer for MIT physics professors, but I will say this is really generalizes across MIT. I won't say whether it applies in Padova. And these 5 bullets are, I would say, ordered in importance. At least in my experience in the MIT physics department, the most important reason why faculty start building digital tools is the realization that using these tools, they can make a better classroom experience, a more magical experience in the classroom at MIT. But once you have digital tools, you can share them with the world, and that means you can share your perspective on how to learn Maxwell's equations with many people around the world whom you will never meet. So that expands the reach of your ideas, bringing the best of the content of what we teach to the world. This is also a motivation. But for most of the faculty I know, it's the second motivation. And then the third, which is related to the second, is to build one's impact either within your field or more broadly. And then the last, and this will be, I'll give a great example of this. My last example will come from the MIT economics department, not physics. In some cases, the motivation for building MOOCs has been to use them as in a way that brings great students to MIT who wouldn't otherwise have found their way to MIT. I'm going to give an example of that from the economics department as my last example. So I told you none of us were ready for March 2020. But in this one respect, the fact that MIT physics faculty and MIT faculty more broadly had been thinking about blended learning, had been developing and improving blended learning modalities for 20 years, had been building MOOCs for a decade, did give us important preparation for March 2020. The other thing which I will mention, so at MIT, there was an Office of Digital Learning that is a decade old. Here, it's the Teach for Learning. Did I get that name right? It's Teach for Learning, right? And that's a great name, actually, because the point is the learning, not the point is the learning. So Teach for Learning to me is a great name. We should have called that, instead of saying the Office of Digital Learning, we should have called ours Teach for Learning. But anyway, but the one organizational innovation I will mention that I think turned out to be very important is Digital Learning Lab Fellows, or DLL Fellows. And the idea there is that we, for a decade, have been hiring a group of educators. Each one sits in a department, so there are 2 in the physics department, 2 in the math department, economics, political science, philosophy, chemistry, biology, and each of them has a PhD in their discipline. One of the things about academics is that we are tribal. If you want biology professors to pay attention, the person telling them how to teach had better have a PhD in biology. It doesn't work well if you have someone with a PhD in philosophy telling the biologist how to teach, or vice versa. So you allow the biologists to hire a digital learning lab fellow in biology. They will pick someone with a biology PhD. But then if you have one actually there are 3 in biology. If you have 2 or 3 digital learning lab fellows in a department and they're isolated, that won't work. And so what the Office of Open Learning does is to create a community which brings all those people together once a week. So the person in math can learn from the experience of the person in biology, and vice versa. All of this we had built over a decade, and in 2020, they were unbelievably helpful to all the professors across MIT because they had the experience that was necessary to help with everything when we had to start over again from scratch in 2020. So with this as introduction, what I want to do in the main part of my presentation is give you 6 examples. I'm going to come back to this slide 6 times. There are 6 examples on this slide. I'm going to tell you about 6 very different modes of blended learning. In each case, I'll try and draw a lesson, or several lessons. In the middle 4, not the first and not the last, I will show you what the MIT student sees. I'm going to go live to the materials as you would see them if you were a student at MIT. The first 5 are from physics, the 6th is from economics. So for the first example, this is one of our earliest MOOCs in physics at MIT was Intro to Atomic Physics for beginning PhD students. So in the Italian context, this would be second-year master's students. So this is not for students fresh out of high school. This is for second-year master's students in Padova, first-year PhD students at MIT. Wolfgang Ketterle is an atomic physicist at MIT. He is a great researcher. He has a Nobel Prize to show for that. He is deeply respected within the MIT physics department for his research, for his collegiality, and because he's a really great teacher. One of the things that I did back when I was associate head of the physics department in 2012 was to go to Wolfgang and see whether he was interested. He was, and he built a MOOC, and then he started using his MOOC, the elements of his MOOC, in a blended learning mode to improve the experience, the educational experience of the students in his classroom. And he was a great change agent in the physics department because the physicists of the world and MIT have a lot of respect for Wolfgang. And when Wolfgang says things like this, they listen. So this is a little video of Wolfgang, and you can imagine him speaking to faculty in the physics department as follows.
Having the students watch the video lectures completely changed the dynamics in the classroom, because I felt I no longer had to teach the material. I could meet with the students and discuss the material. So for me, I have to say, the residential course with the online material was for me a transformative experience as a teacher. The experience of the flipped classroom, which means I use online lectures, but then use the classroom time for discussions, has changed my experience in a number of ways. One is, I've never ever had a class which was so interactive. The engagement of the students was for me unprecedented. Another aspect which was different for me is how I felt in the classroom. The students can observe a working physicist, a physicist in action. I think video lectures, segmented video lectures, online concept questions, online problems are wonderful elements, and they should be integrated into the classroom, but really balanced with the personal face-to-face and interactive experience.
So that's a perfect synopsis of what I've been talking about. I think it's from 2013, that video. It's about a decade ago. And in that case, the magic is simple. The magic is the experience of being a student in that classroom, having a discussion with Wolfgang in that classroom, asking him questions, him asking you questions, and the discussion that he described, that's the magic. So my next example will come at the very beginning of the university education in physics at MIT. And I'll spend, this is the example I'll spend the most time on, actually. We teach every MIT student 2 semesters of physics. First semester is called 801 and is Newtonian mechanics. Maybe here it should be called Galilean mechanics. The second semester is electricity and magnetism, and that's a class that I teach. We have a 20-year history of blended learning in these classes, and this has been the way that many MIT physics professors have been exposed for the first time to these modes of teaching, because so many faculty in the department are involved. Every academic year, we have probably more than 10 faculty in each semester are involved in the teaching of these 2 very large subjects. MIT has 1,100 students per year, and they all take both these classes. There's a delay here. There we go. So this is a little video from 2014 describing the active learning classroom. So this gives you a sense of the kind of engagement we're trying to create in the classroom when we're teaching kids who've just arrived from high school and they're in their first physics class. That's the classroom in which I teach, and it is as chaotic as that, almost always. I'm going to ask you to get your clickers out and try your hand at this concept question. Okay, so the most popular... Oops, sorry. I didn't mean to do that. I'll go right here. Sorry about that. I'm going to ask you to get your clickers out and try your hand at this concept question. Okay, so the most popular answer only has 50% of you, so please discuss among yourselves, and then if you would like to re-answer, go ahead.
Well, I mean, if the charge has like an initial velocity, then it wouldn't follow.
Or it has a mass.
Pay attention to that person on the right there. I'll tell you who she is in a second.
If you were to take your hand as an arrow, and you're the point, which way would you point to get the Earth's magnetic field in this room?
Okay, that's great. Your discussions, you're now at 93% on the right answer. So by talking to each other, you went from 50% right answer to 94% right answer. So the person I said I would tell you who she is, her name was Elise. She was one of my undergrad TAs in 2014, later did a PhD in linguistics. In that classroom, if every seat is full, there's 108 students, and there's me, or Peter Dermashkin was the other instructor that you saw. But the key thing is we have 7 or even 8 undergraduate teaching assistants like Elise, whom I showed you there. And I teach them to teach the students, and in all of those moments when the students are wrestling with doing a problem at the whiteboard or answering a clicker question, my undergrad TAs are interacting with groups of 3 students and asking them Socratic questions, engaging with them. The magic there is the 3 18-year-olds learning how to collaborate, learning how to interact with each other as peers, and being prompted by that teaching assistant or me. I can't interact with all 108, but I make sure that every student that there's a teaching assistant who interacts with every student in every class, in every class session. And I interact with as many as I can. So 802, there's more than 800 students in the spring, about 200 students in the fall. We embraced this active learning model a decade and a half ago. This was what we said in 2014. Now it's been 20 years. And more recently, we built a MOOC out of it. There is now high levels of student approval for the online elements of this course, and in particular for the online rapid feedback that students get by doing problems online and getting an immediate sense of whether they've gotten things right or wrong. So as of 2014, what we had focused on was these auto-graded problems. But the biggest challenge as of 2014 remained, frankly, students not doing the work before coming to class. The key to create this engagement in the classroom is that before the students come to class, they should have already had a first cut look at the content. And our students weren't reading the book. You know, we'd give them material in old-fashioned ways, and they weren't reading the book. The pandemic prompted us to sort of complete this 20-year process of transitioning to a blended classroom mode, and I want to switch now to this screen. So if you were an 802 student right now taking the course this semester, I'm not teaching it, I'm on sabbatical this semester, but this is a course that I teach. This is the online component of the class. So here's week 6. Week 6 has 2 classes, week 6 day 1 and week 6 day 2. And before you come to class, you're supposed to do 2 learning sequences. Let's look at this learning sequence. So a learning sequence has, actually, I want week 6 sequence 3. I picked the wrong one, sorry. Week 6 sequence 3, here it is. So it has videos. So I'll just play a little bit of this.
This is the moment when we introduce magnetic fields. 802 is about electricity and magnetism.
So the first time they see magnetic fields is not in the classroom, it's in this video.
About magnetic fields.
Now I'm not here to teach you magnetic fields, so we'll skip ahead.
The first step towards magnetic fields that we took was the moment when
Oh, and one of the great things about this is that when students are watching your video, they can stop it, they can go back, or in this, they do a lot.
We started to allow charges to move.
They can say, oh, this is too easy, I understand this, I'll play the professor at 2 times speed.
We've been talking about conductivity, resistivity, understanding how conductivity is related to microscopic properties of a material.
Students do this all the time. I run into students at MIT and they tell me that I talk much slower in real life than when they listen to my videos, because most students watch the videos at 1.5 times speed.
Charges start to move. Although we didn't stress it until paradoxically,
giving you a sense,
of this compass needle
giving you a sense, giving you a sense.
A rotational problem of this type.
So that's a 5-minute video, which I won't show you all of. Then here's another 5-minute video of a different type.
I could separate them.
This is one where I'm doing an experiment.
I've got a magnetic north pole and a magnetic south pole. Let me try and separate them and see whether I get 2 isolated Coulomb magnetic charges. So I'm going to break this magnet. And
so this is a really important physics lesson. What happens when you break a magnet? And they see this for the first time before class. And then we do it again in class, and we have them do it.
And now let's see whether I get 2.
Again, I'm not teaching you physics here. I won't show you the whole video. And then we give them problems. And these are intended as relatively straightforward problems. Which of the following statements is true? It turns out 2 and 5 are true. I did this before class. If you miss this, you get 5 attempts. If you miss it after 5 attempts, we give you a second chance. This is new this year. Click here to submit second chance responses. The idea here is you're puzzled. When you click for second chance, you get to see the solution, and then you can get full points. You get a small amount of points for each problem. You can get those points by submitting a written reflection in which you reflect on what you didn't understand. And what's really cool about this is that then one of the Digital Learning Lab fellows has built an AI routine that takes all those second chance responses, all those reflective comments from the students about this is why I didn't understand it. And we have an AI routine which distills that into something for the professors for the next morning, which tells the professors these are the things that the students aren't understanding. Then I come to class and I can focus on those. That's actually new this year. So another video, another problem, another video, another problem. This is one learning sequence. You do 2 learning sequences before coming to class. I want to show you a couple more examples, but you can ask yourself, does it actually work? And I'll tell you how I know it works in a minute. By does it work, I mean, do the students actually do the work before they come to class? Before I do that, I'll just show you after you come to class, week 6. After you come to class, you do a problem set. The problem sets have much more sophisticated problems. This, again, is not a physics class, so I won't ask you to read the physics problems, but these are more challenging problems. This is something you might work on as a first-year physics student. You and your friends might work on this for 3-4 hours, this problem set. And these are answer checkers. What that means is you can type in an answer here and see whether you have the right answer. So we don't actually grade for whether you have the right answer. After the problem has been, the due date has passed, and you've turned in your solutions, we reveal the solutions. Here's the solution to that. It took that much to write out a solution. The students actually get the credit not for getting the answer right, but for writing a correct solution, a correct derivation. So we've recast what a problem set is, we've recast how the students get exposed to the content so that in class we can have a much more active learning experience. I want to, still in this intro level, I want to give 2 more examples. One, I just want to very briefly show you an example that sets up my answer to the question of does this work. So I'm going to go, this is last year's 802. This is in fact from when I was teaching it last year. And if I go to week 8, sequence 3. Here's a video. It's a fairly long one, actually. It's a 15-minute video in which I'm explaining
where little n is equal to
a pretty complicated derivation.
Of turns
And
per unit.
so this is a long video. It's a challenging concept for first-year physics students. It's how to calculate the magnetic field from a coil of wire.
With 1,000.
I think I explain it well, but does it actually work? I'll tell you how I find out in a second. What we do the night, this is still what you do before class, is we give them a problem which, if you've understood it, you can do this problem. Then they come to class, and I'll tell you in a second how I know that it's working. I keep delaying that because I want to show you one last example from 801, just because this is Padova. So if I go to Newtonian mechanics, I just want to show you that every single MIT student, when they come to MIT and they take this physics class, this is week 1, I have to get the right sequence. Week 2, sequence 1 is what I want. So it's your second week at MIT. You are taking the physics class that everyone must take at MIT. It's the second week, sequence 1, and you get Galileo's piano inclinato. There we go. This is a beautiful problem. This piece of apparatus is from a museum. Sadly, it's a museum in Florence. You should get this. Go steal this apparatus from Florence. This should be in a museum in Padova. And it's a beautiful experimental determination of g, the acceleration due to gravity, which is this method was invented by Galileo. It's actually quite a non-trivial problem. This is a pretty substantial problem that we give to second week MIT students. I just wanted to show this to you because I'm in the auditorium in which Galileo gave his lectures. So let me go back here, and here's my answer to the question of whether it works. So I come into class the next day, and in 2022, I put this slide on the screen at the beginning of class. No preamble from me, no lecture from me. I said, start by going to the board and work your way through this. This is asking them to do what I did in that 14-minute video. And there's some hints. 1, 2, 3, 4 tells you how to walk your way through it. And I can tell you that if I taught this class in 2015 without the MOOC elements, and I taught it in 2022. In 2015, if I started the class with this and said, go to the board, they would have been lost. And the reason they would have been lost is that they didn't read the book the night before. And I can tell you that in 2022, I put this up on the first, and I did it, and I sat back and watched, and in the next 10 minutes, all the students were at the whiteboard. They were in their groups of 3, and they all worked through this. For any of you who care what the solution is, this is the solution to the problem. This is what I taught them in that 14-minute video. But you don't show them this until after they've done it. And I walked around the room, and there were correct solutions on all the boards, and that's what I had done in the video, or they had seen in the video the night before. So I can do this every class. I can check whether they have done the learning of content before coming to class, and it actually works. And it never worked when we gave them reading. It works when we give them learning sequences. So. And here's an example, by the way, of the kind of feedback that the instructor now gets. So last night, the students were wrestling with one of those learning sequences. A bunch of them did not succeed in answering questions. They provided reflections about what they had missed. The AI routine distills those reflections and tells the instructor, here's 4 things the students are confused about. So in class the next morning, I can make sure to create discussion, conversation about these 4 questions. The students never see this slide. This is something for the instructor. Okay, so that's my most extended example. Of the other examples I will go through much more briefly. I wanted to give you other examples at other levels with other goals and other purposes, but I will not do so at the same length. So next example, completely different character, of course. These are juniors, which is 3rd-year undergraduates. And this is an experimental physics class. This is a rite of passage at MIT. It's the class where students learn how to do experiments. And they spend hours and hours and hours in the lab wrestling with the apparatus. You can't do this online. So what am I talking about, an experimental physics class with digital tools? Well, this is the learning management system page, and as you look at all the materials here, you will find the pre-lab write-ups, which any of us who've ever taken lab classes know what pre-lab write-ups are. But then you also find these sequences on working with data, introduction to scientific notebooks, oscilloscopes, Poisson statistics, curve fitting. And in each one of these, if I go inside, I find little bits of MOOC material. Sorry, this is just a PDF. I clicked on the wrong button. If I go inside there, you find little bits of MOOC material. There's a little mini video. There's a problem. There's another problem. That's a little chunk of MOOC in the lab class. And what the professors who teach this lab class have realized is that if you want to teach your students curve fitting or data analysis, to do it in lecture mode is the most boring thing imaginable, because you're doing it in the abstract. Students don't care about curve fitting until it's 2 in the morning, the lab report is due the next day, and they need to fit a curve. That's when they care about curve fitting, and you're not there. So the instructors of this class have created these little mini MOOC-like very small nuggets of MOOC-like material so that our students have it when they need it, which is invariably 2 in the morning before the lab report is due. So there are also in here, I won't go through it, but there are videos of some aspects of the apparatus also. There's another example, not from physics, in neuroscience, where there are videos of some of the great neuroscience experiments involving sticking electrodes into nerve cells. There are videos of those being done which serve as preparatory material for the students who will then try and do it themselves the next day. So there are lots of ways in which people, even teaching lab classes, are using these techniques to improve the preparation of the students either before or after they come to lab. Third example, quantum physics. So this is a more advanced class. This is a class that is taken by third-year undergraduates again, and the production value is a little less here. If I just play a moment of this video, this is just a video of Barton teaching in the classroom.
Just straightforward. So, what is T x0?
I'll stop that. This was just this is a standard classroom. It's a video of Barton. This was not prepared for the purpose of on an online modality. It was a videotape of him teaching in an ordinary classroom. So for these more advanced classes, we put less into the preparation of the materials, but we put more into the preparation of the problems. So I have to find the right place here. If I go to week 6. Week 6, lecture 11. I'll just give you an example of a more complex problem type. It's not multiple choice anymore. There is a mathematical theorem with it's Swiss cheese, 1, 2, 3, 4, 5, 6, 7 holes. And here's 1, 2, 3, 4, 5, 6, 7, 8 things, either the number 0, 1, 2, 3, or 4, or the word complex, or the word imaginary, or the word real. You have to put the right thing in the right hole. It's basically impossible to do this unless you understand what you're doing. There's far too many wrong choices. There's a vast number of wrong choices. So this is an example of a problem type which is not hard to build, but it's much better than multiple choice. We use this kind of problem type a lot in our more advanced classes where you're trying to teach students to think through more abstract proofs. I think what I'll do actually is I'll go to the next example, which is an even more advanced class. This is a class that Francesco has taken from Ian Stewart. before Ian built his MOOC. This is a course for second-year PhD students. Were you a second year or a third year when you took it? Third year. So Francesco took this when he was a third-year PhD student. The videos now in this, so there's a MOOC for this course. The videos, this is a 45-minute video. That's bad practice. That's bad practice, but it's much easier. We just videotaped Ian teaching in the classroom and put less time, because these are PhD students. If they're motivated, they will watch a 45-minute video. We put a lot more into the problems. If I go to the problem set here, I'll just show you the solution. So if I go to the problem set, this is the homework. The statement of the problem takes this much. Okay, that was the statement of the problem. If I do show answer, just give you a sense of the solution. That's the solution to part A right there. Okay, so this is what Francesco learned when he was a third-year PhD student. Ian, one of my colleagues at MIT, built this MOOC not long after Francesco finished his PhD, around 2014, 15, in that range, 16, he built this MOOC. In the classroom at MIT, Ian has taught this class to Francesco, and he teaches this class about once every 3 years. He gets about 5 to 8 students, so think of it as 20-something students per decade. When he runs his MOOC, he reaches 50 to 100 students each run, and there are graduate students in theoretical physics whom he finds by sending out an email to 1,000 theoretical physicists on an email list that he maintains, saying, I'm running my MOOC again, have your students can take it. So Ian Stewart has just multiplied his reach and impact in theoretical physics enormously by conveying his perspective on a very advanced subject, not just to 20 MIT students per decade, but to 100 theoretical physics students per MOOC run, 50 to 100. This is an example of the kind of reach and impact that motivates faculty to build MOOCs. So, okay, here we go. One last word about the fourth example, the quantum mechanics example. Why did Barton build this? Barton Zwiebach is the professor who built this. This is the answer to Francesco asked me, what is 8051? So 805 is the number of this class. We, since time immemorial, have taught this class only in the fall semester, not in the spring. We now teach it in the spring also. We don't have the staffing to do that, but we use the MOOC in the spring. So in the spring, which is 8051, the students learn all the content from the MOOC materials, and then they have a discussion section with Barton or some other professor twice a week. And that's the way we teach this class in the spring now. So if you want to take the class with a traditional lecture, you take it in the fall. If you want to take it in a blended learning mode, you take it in the spring. And we have about equal numbers of students now taking it either way. So let me close the physics part of this with a video in which I will let Barton and Ian speak to you themselves. This is a video that we made as part of the celebration of the 50th anniversary of the MIT Center for Theoretical Physics in 2018. I won't play the whole thing, but I want you to hear from both Ian and Barton. So let's listen.
So here we go. I've been a faculty member in the Center for Theoretical Physics for almost half of its 50 years. When I was offered the opportunity to become MIT's new Dean for Digital Learning, a big part of how I thought about the role came from my having watched the remarkable things that my two CTP colleagues, Ian and Barton, have been doing with digital learning over the last few years.
Effective field theory is an important advanced topic.
So this is the PhD level
students
class that Francesco took in the classroom.
In a regular course curriculum. In effective field theory, we build quantum field theory that is specially designed to study physics at a particular distance scale while systematically retaining information that is needed for higher precision. My goal in designing the online course 8.EFTX was to take a unique special topics course taught at MIT and make it available to researchers and graduate students from around the world. Since the MIT course is not offered every year, the online version also provides a resource for our graduate students to learn the material. In this way, the online EFT course serves as a repository of information about effective field theory that can aid people's research in high-energy physics, nuclear physics, and other disciplines.
I've always felt it's a privilege to be able to teach quantum mechanics to young, enthusiastic students. We at MIT are a little different. We give 3 undergraduate courses in quantum mechanics. This gives our juniors and seniors a very strong preparation that allows them to do undergraduate research very effectively. Our online efforts aim to make the teaching of quantum mechanics better at MIT, and we also want to share what we learn with the whole wide world. The technology is amazing. We can teach these courses without any compromise. The online courses are as difficult and as challenging as the MIT courses we teach. This online grader is quite amazing. It allows you to check for complicated formulas and even graphs of functions. We don't need anymore to have multiple choice questions. The problems are sophisticated and address all kinds of important issues.
Okay, so that gives you a sense from the 2 faculty. These courses are just as rigorous online as they are in class, but they don't say it in the video, but they're missing the magic. So you're getting the same problems that the MIT students are doing on campus, but you don't have the interaction, you don't have the human aspect of learning. That ends my 5 physics examples. I'm going to end the talk with an example from economics. I will say that blended learning and activating the classroom, there are examples across MIT. I've chosen the physics examples because those are the ones I know best, but there are examples for many other disciplines. To close the penultimate part of this talk, the idea of blended learning is to create the space and time for engagement so that magic can happen in your classroom. We in physics at MIT have 2 decades of experience of sharing the content of what we teach with anyone. We've done that through OpenCourseWare for 20 plus years, and now with our MOOCs for more than a decade. And more people are doing variants of this, and it's very easy now to make lightboard videos of the kind you saw from me when I was explaining magnetism. Auto-graded problems of simple types are straightforward also. The more challenging, more advanced problems are a little harder and are where we invest a lot of our time and energy. So this gives you a sense of what I mean by from MOOCs to magic. The MOOCs are allowing us to share an aspect of what we teach with the world, but at the same time, the elements of the MOOC are being used by our students at MIT before they come to class and after they come to class, allowing us to make the in-class experience magical. Blended learning is just one way in which we're using things we learned in getting through the pandemic to improve on-campus education. I want to end with what is perhaps the greatest single example I know of from MOOCs to magic, and it comes from the MIT economics department. It's an entire program called Data Economics and Design of Policy, or DEDP. It's built, these economics faculty, I'm not sure if there are economists in the room. If they are, look at the names on the right. Those are 8 great MIT economists. There's 2 Nobel Prize winners among them. They have built 8 MOOCs on microeconomics, running randomized evaluations, data analysis for social scientists, and the other subjects you can see there. And now, why did they do that? I'm going to play the video from Esther Duflo so you can hear this in the words of the economists, and then I'll show you the last few slides.
Poverty, access to education, malnutrition. These are just some of the most pressing problems facing countries across the globe where poverty is massive and persistent. High-income countries grapple with their own set of challenges: slowing economic growth, income inequality, climate change, to name a few. There are thousands of policies and programs all over the world dedicated to solving these challenges. But how do you evaluate their effectiveness? How do you ensure that policies designed to tackle these problems are backed by scientific evidence? And how do you determine which methods are most useful in effectively addressing problems facing disadvantaged populations? MITx MicroMasters program in Data, Economics and Design of Policy aims to equip learners with the knowledge and the skills to approach these pressing challenges.
Using cutting-edge research from Nobel Prize-winning faculty that places an evidence-based approach at the forefront of policy design and evaluation. All the content in these courses is developed and delivered by MIT Department of Economics, rated #1 in the world. The content in each DETP course balances theoretical knowledge with practical skills, combining tools in program evaluation and policy design with a deep understanding of the economic and mathematical principles behind them. Taken together, these courses provide a rigorous foundation in microeconomics, data analysis, probability and statistics, development economics, and program evaluation.
This is a series of MIT caliber courses, so you can expect that the course load will be demanding but rewarding. DETP learners who successfully pass 5 courses, including corresponding online proctored exams, earn a MicroMaster program's credential from MITx. Depending on the courses you complete, you can earn a credential in International Development track, the Public Policy track, or both. Whether you're already a researcher or a policymaker, or you're interested in starting a career in policymaking or pursuing graduate school, this certificate will provide you with a strong foundation on which to take your next step.
MicroMasters credential holders who apply and are accepted will be recognized as already having 1 semester's worth of credit.
So accepted students will earn MIT credit for the classes that they completed online and will be able to pursue an accelerated master's degree here at MIT.
While the MicroMasters is comparable to an entire semester's worth of advanced MIT.
So that's the magic. In this construction, you start by, this is a slide that you saw on the screen, in the video, you start just with online work, and this reaches students who would never have had access to this content before this series of 8 MOOCs were built. These are students who are very often working in the Ministry of Food and Water in a developing country, trying to do a better job of advancing the economic development of their country and wanting to use rigorous economics but not having access to it. That's who Esther and Abhijit and colleagues are reaching. And if you pass 5 exams from 5 of the 8 courses, you get a MicroMasters credential. But then, and that's great, that's reach, that's impact, but it's not the magic. The magic comes from the last thing that was said. Actually, before I go to the magic, just to talk about reach, they have reached 350,000 students, 10,000 of whom have completed at least 1 course, 1,000 of whom have completed the entire MicroMasters. 69% of those participants are from low to middle income countries. Then you can apply to MIT. And if you're admitted, you come to MIT and spend a semester at MIT and you leave with a master's degree in half the time. The MIT Economics Department never had a master's program before this. Master's programs are unusual in economics departments in the United States. They created this master's program with this structure. Only holders of the MicroMasters can apply. They come to campus, and you end up with 20 students per year coming to MIT who would never have been at MIT before. These are amazing students. Their performance is spectacular, but their trajectories are such that they would never have come to MIT. We don't normally attract civil servants from the government of India. We don't normally attract a student who completed all of their education in Somaliland. Now, 20 students like this are coming every year, and what the MIT economics faculty say is that this is great for the education of all the rest of MIT's economics students. In the classroom at MIT now, the magic involves a bunch of students who are admitted the normal way, very often American, almost entirely first world. Plus, these 20 students who were brought to MIT via having shown their capability through the online work, and this increases the authenticity of the educational experience of the other students, because these students have a real-world life experience that adds to the economics education of everyone they interact with. And this is not me speaking, this is the MIT economics department speaking. I'll give you a quote in a second. So this is just to show grade performance in an econometrics course. This is something they take on campus. It was not part of the MOOCs. And the MicroMaster students did better than the normal MIT students. So these are really good students. They did great in their courses at MIT, and their MicroMaster's performance was a good prediction of their MIT performance. But I will end with these 3 quotes. I don't have them in video form. The top quote is from Josh Angrist, a Nobel Prize-winning economist at MIT who had nothing to do with the building of this MicroMasters, but sees these students in his classroom and says, they're great students. The bottom quote is from Daron Acemoglu. I predict he will win a Nobel Prize soon. He's an institute professor at MIT. And he also had nothing to do with the building of this program, raves about it because he has had these students do research with him while they were at MIT as master's students. And then the middle quote is from Sarah Ellison, one of the builders of the program. And she speaks to the increased authenticity of the learning experience of the rest of MIT economics students and says that the DETP students come to campus with such varied perspectives and experience that they bridge the gap between the economics classroom and the real world. Their contributions enhance and deepen in-class discussions and enrich the social fabric of the whole institution. We just love having them. So this to me is an amazing example. You start with 8 MOOCs and you create more magic in the MIT economics classroom for all of the MIT economics students. And they boasted in that video that they're the #1 economics department in the world. They are. And for them to be saying this shows that this kind of thing can make a top department better. And that's what they're saying. So this, I think, is the best example I know of from MOOCs to Magic. I wanted to end with it. It's quite different in character than anything we've done in physics. I think the blended learning is something that's being done across MIT. I gave you the physics examples, but I wanted to give credit to the economists of MIT for this amazing thing that they have done, and I will end with that. So we will take questions as a panel. I think now we gather as a panel, if I understand correctly. Is that right?
So welcome to this roundtable discussion session, and maybe we can start our conversation. I wonder if it's possible maybe just to make a short introduction, then I'm going to pose some questions to our guests. It was, of course, a pleasure to start the discussion exploring the intersection of digital tools and learning experience, and we are really honored to welcome our distinguished guests. In a rapidly evolving educational landscape, the integration of digital technologies has become fundamental in redefining the way we teach and learn at university. We heard about this passage from MOOC to the magic, and probably we also discussed about innovative technological platform that they are going to offer different experience to our students. However, I would like to take a brief journey into the past. approximately 250 years ago. In the upcoming spring of 1774, Jean-Jacques Rousseau, the Swiss philosopher of education, often hailed as one of the most influential figures in modern teaching, sat at his desk. It was during this period, the last period of his life, that he wrote the 7th letter of a series of 8 letters to Madame de Lessert, and a very close friend of him. Madame de Lessert asked Jean-Jacques Rousseau for his guidance in educating a young daughter about the science not of education, but the science and the joy of botany. So, Rousseau, the écolier, the scientist of education, known for his innovative approach to scholarship and his challenge to traditional methods of instruction through experiential learning and hands-on experience, find himself compelled to experiment with distance learning experience 250 years ago. He needed to find a way to teach and learn through remote interaction, as he was unable to directly engage with this young pupil. So Rousseau, one of the founders of the modern teaching methodologies, emphasizing student-centered approach, active learning, and the holistic development of learners, echoed the challenge that we are facing today here inside this room with the question of how to effectively facilitate learning in non-face-to-face environments. And looking ahead and 2.5 centuries, the question of how to employ pedagogical practice and tools to tackle the challenges of education remain as relevant as it was before. So I have the honor to moderate this session, and so with great pleasure would like to introduce our esteemed speakers. Well, of course, Professor Rajagopal, but also I would like to introduce Professor Mauro Calise, and is Honorary President of Federica Web Learning, University Federico II of Naples, and also Professor Carlo Mariconda, Advisor of Digital Teaching at the University of Padova. And I'm sure that their contribution will enrich this session. And of course, I would also invite you to participate to this discussion with reflection, question, and your insights. So I would like to start maybe with you, Professor Mauro Calise, and probably your platform is one of the largest platforms in Europe regarding MOOCs production, and not only. But many things are happening now in Italy, starting from the hub we were discussing before. So I'm asking you something about the relationship between, of course, artificial intelligence and education. What do you think are the effects on teaching practices?
Well, thank you. Thank you for inviting me here. And thank you for listening to this very interesting lecture about the MIT experience. MIT has been a leading experience worldwide for decades, and we hope it's still going to be like that. Though the whole situation is getting more and more complicated in terms of how much we can master of the overall experiences and bring them to some kind of coherent, cooperative effort. Because in my view, that's one thing which is unique and exceptional with digital education, is that it can go beyond individual universities and bring universities together in some kind of partnership. This has been a very important experience with MIT and Harvard in the past, and you have been a front runner in this respect. And this, we hope, may be an experience in Italy as well. As I am more than speaking about what we've been doing with Federica in the past years. I hope that we'll be doing together. We are just now building a network of 14 universities with the Digital Education Hub. It's the first chance that something like this may happen in Italy. And we've been already starting to work to try and bring together. You know, I am a social scientist, political scientist. So basically, we are comparativists. We always work through examples, patterns, and possibilities of learning one from the other. And this has been our past experience at Federico of the University of Padova. So one of the first things we've been trying to do is what's coming next? Are we doing MOOCs together? And of course, the kind of experience that you have been showing us is incredibly important and profitable to take patterns of past experience and try and translate them in our own models. That's one of the main aims of our Digital Education Hub, is just coming up with common patterns among universities as different as Padova and Naples and Florence and Sapienza. This would be a major breakthrough for Italy. So common patterns, and we look very much forward to continuing this cooperation. We can see this as the beginning of some new transatlantic form of a cooperation. We have learned so much. We are, of course, latecomers, but as latecomers, we may have some of the enthusiasm which is necessary in this kind of experiences. And of course, in looking into new models, we also, I mean, at least personally, I was curious to take one first, I wouldn't say systematic, but very rough bird's eye view about what's the state of the MOOCs today. I mean, you know, MOOCs have been exploding, and then at some time it looked as if we were entering like a phase of decay, at least with respect to the expectations. You know, I always remember Christensen's article on the Harvard Business Review about MOOCs as a disruptive innovation. It turned out to be a little less disruptive than we originally anticipated, but who knows that artificial intelligence may not bring new life and energy, especially from one aspect of which I want to just spend 3 words, and then we'll move to the numbers, some very rough numbers that I prepared for this presentation. But MOOCs have been basically a top-down phenomenon. Inspired with all the blended with all the participation, which has been extremely important, and it's become more and more important. But you may remember, of course, that in the beginning there were 2 competing models about, you know, the building of MOOCs. The constructivist model and the one which has then prevailed, which is the, you know, so is there something that we all build together? Or is it something that the most established universities produce and then, in a way, convey to the millions of students, over 350 million students on the MOOCs platform? It's a fantastic result. But basically, it's a top-down process. Now, one question, is it still going to be the case? Do we expect artificial intelligence may become a tool through which personalization of the teaching experience will be growing? This, to me, is the major question that we are going to face. And of course, I do not have the answer. This would be a fantastic challenge to undertake, all of us together. I may simply now try and give you the numbers because I was curious to see myself. So now, how many MOOCs are we still talking about now? What are the main characteristics? And how all of this relates to the universe of artificial intelligence. So, do we have the numbers there? Yes, that's it, I think. Do I do this or that?
Yeah.
Oh, that's it. Good. So basically, oh yeah, that's funny. That's 22 million occurrences if you look for a Google query, online courses and artificial intelligence together it was 30 million the day before. So clearly this number changes very rapidly. But this is not an important number. It's still a pretty, I would say, striking number. This is all kind of material. It's just courses, seminars, webinars, whatever is related to the combination of online courses and artificial intelligence. Now, basically, we have a total of 1,611 teaching projects, courses, programs, which concern AI. When I mean concern AI, I mean which do present in the title description skills at least one of the following keywords. These are the keywords we have considered as associated to some extent to AI. And it's a huge percentage. I mean, it's about 60%. So basically, the MOOCs teaching universe is by almost 2/3, somewhat AI related. The sample was limited to Coursera, edX, Udacity, and FutureLearn. So basically, the Western providers. It would be very interesting to compare this with Chinese and Indian platforms, which have been growing enormously in the past 5 years. Now, this almost 1,000 teaching projects comprise basically 2/3 are courses, individual courses, and then projects or guided projects, programs, degrees. Over 80% of our courses are in English. Second languages are Chinese and Spanish. This is, of course, one thing that at the Digital Education Hub we are working at with Florence, Padova, Sapienza, and the other universities. Translation is going to be a major novelty. I mean, clearly there are now the elements for having courses translated in all possible forms, I mean, with subtitles or just the audio and whatever else. So this is going to be a big frontier. Over 75% of the AI-related courses fall in the computer science and IT category. So again, that's a real hardcore. It's interesting to see the second in the list is philosophy and ethics. So clearly that's an important subject for this kind of courses. But again, I was surprised myself. We are moving, at least as far as the open access digital education environment, towards an environment where AI-related material are extremely hegemonic, to say the least. A large majority of beginners and intermediate courses. And so that's also important to see. I mean, it's like, you know, there is a need for learning more and more and more. And we could enter in 4 of these. It's interesting, we have 2 Spanish courses, and the numbers are already very encouraging. I mean, are not the million of people, but you can see we have enrollments in these 15 courses, which are focused on education and teaching training. So basically, the idea of courses which are specifically targeting the problem of how does artificial intelligence relate to the education and teaching training. So I think this is a very, very important frontier where we all should try and meet the challenge of the future digital education. One methodological note, I mean, this is an excerpt from a 40 pages report that we did, of course, with ChatGPT assisted queries. It was extremely fast and easy. I mean, in this respect, it was an incredible improvement with respect to the kind of queries he would have been doing before. And so it's only the beginning, but we can see this thing is really coming very, very, very fast. And I hope we'll be together on board in this effort real soon. Thank you.
Can I make a couple of comments?
Oh, yes, of course, please.
Yeah, so thank you very much. This is great and very impressive. I think one of the real frontiers and challenges is how we can share MOOCs as educators, and you were alluding to this. For me, a big part of the value of MOOCs is using MOOCs in our on-campus learning, and I will say, it's even a challenge at MIT for Professor A to use the MOOC prepared by Professor B when they're both MIT professors. But what we haven't really learned yet is how to use pieces of MOOCs that were developed on the other side of the world in our own classroom. So in other words, how to create a context for the sharing of these digital tools so that something that is developed in Padova can benefit students on campus in Naples or vice versa. So if in the context of the network that you're developing in Italy, you can, which is built upon what you have led for in such an impressive way, if you can show all of us how to build a sort of a sharing ecosystem, I think that will be a big advance. I see the challenge of that even within MIT, sharing among professors in MIT. I also want to say a couple more things. I find this, you mentioned this notion of disruption. I find that sort of humorous, particularly sitting here. This university has 800 years of history. Gutenberg's invention of the printing press did not disrupt this university. It made it better. One could imagine people at that time saying, "Oh my goodness, this new printing press thing, you won't have to come to the university to meet the printing press is going to change everything." It of course made universities better. This too will make universities better and already is. And I hope same with AI. I'm not an expert on AI. But I think the examples that you gave show the importance of MOOCs in a lifelong learning context. I mean, these new to AI technologies are new. Students at our universities are learning about AI in the classroom, but 15-year-old kids want to learn about AI. And people who are 20 years beyond their university education, they're in the working world, they want to learn about AI. And so it highlights that one of the values of the MOOCs are to reach people who are not in the stage of life when they can come to a university as an undergraduate or a master's student, but there's something that they want to learn, in your example, AI. The other side of AI, which I don't think exists yet, and I would love to hear, none of us are computer scientists, but if I think about my undergraduate teaching assistants, whom I showed in that classroom, they are better than any AI at going to a group of 3 students wrestling with a problem, seeing what they've written on the board, saying, "Why did you do that? What did you mean when you went from there to there? Did you think about whether instead there was some other way of thinking about it?" Of looking at what, and then having a dialogue, getting a sense of what those 3 students do and don't understand, probing them, teaching them to think for themselves. That's something we as educators pride ourselves in knowing how to do. I think the undergraduate teaching assistants in my classroom do it better than any AI that exists today. And I think there's a real challenge there, which large language models, which are justly creating a lot of excitement, don't do anything like what I just said. They're not set up at all to do what I just said. So I think AI is revolutionizing how we do all kinds of activities, but I don't actually yet see it affecting teaching in the most elemental sense, which is 1 teacher, 3 students, or 1 teacher, 1 student with a dialogue and questioning which focuses not on content but on learning. What I teach my TAs is that your focus should be at what do the students already understand, what do they not understand, and your goal is to help them to learn something. It's not to convey your job is not to convey the content, it's to help them to learn for themselves. I don't see AI that addresses that challenge yet. I'm curious whether you do.
Well, thank you. Also, thank you for reminding us the role of teaching assistants in our classes, which are fundamental, I agree. But I would like now to extend the question to Professor Carlo Mariconda and talking about the learning and teaching experiences as an ecosystem. What is the situation here at the University of Padova? Would you like also to share something about the future, the state of art, but also future expectations regarding our university?
Thank you, and congratulations for your conference. So in Padova, the state of the art, we are in MOOCs since 2014, more or less, 15 maybe. We had agreements with different platforms because we believed that it was important to adhere to different pedagogical models and to learn from these platforms. So one of them is Federica, and another one, EduOpen. It's a consortium of Italian universities, and FutureLearn, which is an international platform which has more or less 18 million learners. We strongly believe that making a MOOC is really important for our colleagues because their courses become open to everybody in the world, and making a MOOC forces you to make a high level quality because you are seen by lots of people. Each of our platforms hosts more or less 30 MOOCs, and we provide exclusive access in some platforms to our students that can take a certificate, for instance, from FutureLearn, and professors may have analytics from these platforms, even from Federica. And what's the operational framework? And so in order to make a MOOC for our colleagues, well, we have a call once a year, more or less, and then we give grants to colleagues that want to make a MOOC, and they are entirely followed by the digital learning office with project managers, and that's a great work. We have multiple recording studios in our universities, so not only the digital learning, but spread all around. We have we saw some light boards, and we have several light boards in the universities. And just a word, because Professor Rajagopal, the title of this conference was about magic. And when we were looking for a light board, it was not possible, like in the US, to buy one. And there were no providers in Europe to obtain a light board. So we decided to make one with our director at that time, Marco Ferrante, and it was really difficult because in Italy we have MEPA, so you have to buy something, and how to buy something that does not exist. So, and fortunately we had the flexibility of our director, and we found a magician that built the structure of our first prototype of the light board. So here was where magic appears. Now we are going towards the National Digital Hub, led by Naples and Federica. So what are MOOCs going to, what is the sense of making MOOCs in this context? Well, as you said, one of the purposes to make to use MOOCs is to make blended courses and somewhat flip the class, even if you don't like that name. But so to have more time in the class, to have activities, and to let students discuss. So this is one of the purposes. One of the strategy of our university here now is to spread, to have more blended courses and even online courses. I just want to speak briefly about two experiences that I have had with my students. I have a blended course and I have an online course. One of the two online courses at the universities is Techniques and Methods in Psychological Sciences. And the interesting fact is that every course in this degree is based on a MOOC. And these MOOCs are hosted by Federica, and they are visible to everybody in the world. So everyone can see what is the content. Of course, in the course, in the real life here in Padova, we do not just use the MOOC, but we do some magic. So this magic is, as you said, to discuss with students, to meet them every week, twice a week, and to organize activities in the platform and so on. The other course that I'm now teaching is a course for engineers. Calculus, second year calculus, and it's a blended course. So I'm trying to, and also 200 of our colleagues now are experiencing blended learning in a traditional setting, among a traditional setting. So use the MOOC in order to study, to prepare the material, and then to come in the class and discuss. And it works. I mean, serious students are very interested in that. They follow the activities, but at the same time, I feel that there is some skepticism from some students, from some colleagues. It appears totally disrupting, I mean, with respect to the past. So, our results are very good, but at the same time, many of our colleagues who are experiencing these new tools and MOOCs and activities and so on face some problems. One problem that mathematicians and physicists know very well is that we have large numbers. So we have classes with about 150, 200 students, and no teaching assistants at all. So this is a question that I'm asking also to myself, how is this model working with these numbers? And the other problem is how to convince our colleagues and students that this method is effective, that is better than the traditional one. And at the same time, when you face lower marks from students, because what we are experiencing is that colleagues that are trying to change actually have a decreasing trend in their in the evaluation from students. So this is a question that I'm asking to you.
So
Thank you.
Well, first of all, I was very impressed with all the things I learned earlier in the day about the ways in which Padova has been leading in what we can call flipping the classroom, and you within Padova. I will just explain to everyone, as we spoke already at lunch, what I don't like about the phrase flipping the classroom. I think the activity is very important and good practice. But the phrase sounds too easy. Here, I'll flip my pen. I just flipped my pen. That was easy. Flipping the classroom sounds like something easy. It's actually not easy at all. To really do it well, you have to go back and think very carefully about what your goals are for your students to learn, and to ask what kind of engagement and interaction you want to create in your students' experience that will allow them to learn. And the learning is not just about content. So in the intro physics classes that I was talking about, and similarly in the intro calculus class that you're talking about, part of our goal is for our students to learn to collaborate with peers. So that's a learning goal, which is not about content. Part of our goal is to teach them problem-solving skills. Part of our goal is to teach them abstraction, in addition to teaching them whatever the physics or calculus is. And so how do you then design? The online part is actually the easy part. The online part is by far the easier part. Lightboards are a good example. We have lightboards in the basement of a certain building not far from where my office is, and if you have an idea and the lightboard is available, you can run down and make a lightboard video, and it's ready for you to share with your students tomorrow. That's the easy part. Online problems take a little bit more investment and effort, but still, that's the easy part. The challenge is that classroom that I showed you with all those students in that buzz of activity. How do you create that buzz? And it's very different for Wolfgang Ketterle's atomic physics students as compared to the 18-year-olds arriving from high school. And so I won't claim to give advice to a math professor in Padova about how to do this best for math students in Padova, but what I will say is, or any students in other disciplines, what I will say is that I really do think it works, and I understand very well why students' first reaction is resistance. It's because we're asking more of our students in the classroom. By making if you're a student, wouldn't you rather just sit back and watch a performance, which is a traditional lecture? That's much easier for the student. You have a great lecture, performance, maybe some jokes. But in an active learning classroom, the student has to put more in and in fact gets a lot more out of it. They learn more, which we know and we can show with data, we can show with exam performance. We have lots of, I gave an anecdotal example, but we have lots of data that shows that our students learn more. And so it takes time, but it took, when we started doing this 20 years ago, it took about 4 or 5 years. We got some really bad student reviews for about 4 or 5 years, but at some point I think there was enough time passed. Students may think that they are radical, but there are ways in which students are conservative, and it took time. But now you don't see students giving us that critique anymore. I think partly it has helped that we've developed the online materials such that those really are supporting the learning in the classroom. So I'm not sure, I don't have a good answer for how to do it with 150 students and no TAs. You obviously couldn't do what I did, but Eric Mazur at Harvard has ways of creating active learning in an auditorium-like classroom with 150 students and no TAs, so maybe you can do what he did. But you have to figure out how you do it with your students, whom you know, and it'll be different in each case. But I would point you to Mazur as opposed to what I showed. And I know that you know what you know, Eric, also. So.
However, the different scale makes the difference, because where you're thinking about a teacher to 3 students is a dream here in our class. It's almost impossible to. So, however, I was wondering about may I ask you, Professor Rajagopal, about the time. Time.
Yes.
You invest to build a course. This is a personal question, but it's a course structured into sequences. Each sequence is made of video, problem. So there is a really a thoughtful design behind it.
Yes.
Can you say some more about this, please?
You mean the time to create those?
everything.
Okay.
Because, a teacher should
Right.
also...
Well, so the time it has taken us, of course, it's taken us a lot of time. We've built up this experience and optimized and improved over 20 years, and really using the online elements for the second half of the most recent decade. So it takes time, for sure. I will also say that those classes are departmental offerings. It is the mission of the MIT Physics Department to train the world's best PhD students in physics who become professors in Padova. It is also the mission of the MIT Physics Department to teach 1,100 undergraduates 2 semesters of physics every year. And that's a collective responsibility. It's not the responsibility of just one person. And so the investment in those courses is quite substantial. We have a lot of faculty who cycle into and through the teaching of those classes every year. And so there's a lot of infrastructure that is built up and that accumulates and is passed from one year to the next. So maybe a better example I can give, I'm developing a new course, which I don't know if this will ever, I think this will happen. I'm sort of part of the way through developing a new course, and I don't know whether I'll offer it as a MOOC first or an on-campus class first. So let me give you the idea for the course first, and then I'll tell you the answer to your time question. So we teach 2 semesters of physics for every MIT student. The first one is Newtonian mechanics, like what Galileo did. The second one, by tradition, it's Maxwell's equations, electricity, magnetism. But why? Why should it be that? What's important, I think, in the second semester of physics is deepening your problem-solving abilities. It's connecting to fundamental laws of nature, and it's building your skills at abstract reasoning, connecting fundamental laws of nature that are about abstract things like magnetic fields and connecting those abstractions to real-world phenomena and technologies. In Maxwell's equations, they govern every circuit in this device. That's what we have done forever at MIT, but it's not the only way. I would like to develop a new second course, which starts out with information theory, a la Shannon, and is much more sort of a computer science-focused physics course. So it starts out with information theory and then goes to entropy and energy. And entropy is just as fundamental and also abstract. It's not something you're used to from childhood. And yet it's profound and important and perhaps more relevant today to teach every MIT student who goes out into the world to answer questions like, we seem to have a problem with carbon dioxide in the atmosphere. Why is it that it seems so easy to pump carbon dioxide out into the atmosphere? Why can't we just grab all the CO2 molecules and put them back in a bottle? Why is it much easier to send CO2 from the smokestack out into the atmosphere? Why can't we build a technology that takes CO2 out of the atmosphere and sequesters it under the ground? The answer is entropy and the second law of thermodynamics. So I think there's another second semester of physics that can be developed, which achieves all the same learning goals, but has completely different content, and would be a better contribution of MIT to the world if we send out technologists and engineers and life scientists and economists from MIT out into the world who have in that second semester of physics learned to think about the climate problem, learned to think about energy. Apparently we have an energy problem. How can that be? You learn from Galileo that energy is conserved. If energy is conserved, why do we have what does it mean we have an energy problem? It must be that there's some sense that there's some energy that's useful and other energy that's useless, and we have, what does that mean? What's useful energy? What's useless energy? It all has to do with entropy and the second law of thermodynamics. So I want to build a new physics class that I think would be a better second semester. And the way I'm starting is building the MOOC elements. I've just given you the vision for half of a semester. I did a first draft of those videos at the Lightboard just before I went on sabbatical. I'm going to refine them this summer when I return to MIT after coming back from sabbatical. I might teach that for the first time next January, the first half of this course. I'll build it out into a full semester over a little bit longer period. Maybe I'll collaborate with some climate scientists and some engineers. The time it took me to record the videos is nothing. That wasn't hard. It's developing the concepts and building the actual ideas for the course. That's the challenge. So the videos is the easy part. The thing I haven't done yet is to build the online problems. But my digital learning lab fellow in the physics department named Michelle Tomasic will help me with that. So you need to have someone who can help you build the online problems. You need to have some infrastructure, and you realize that it's actually not hard.
You need a community.
Yeah, so you need a community. You need an ecosystem. But I don't think the development of a new course like this will be any harder for me than it would have been in the old days when what I would have been trying to create was the lecture notes.
Okay, thank you very much. And Professor Mauro Calise, what about the achievements and maybe the limits that your platform is facing, also according to what exactly Professor Mariconda said, for instance?
Well, you see, the real issue, I think, is that in Europe, we have not been able to live up to the challenge of this open access education. There is an important difference between European and American universities. I mean, there are several differences, of course, but basically, the top US universities are private universities. Mm-hmm. They are private universities in a different way in the corporate tradition of private universities, let's say, with a public mission, but still, they are private universities. And so there is a limitation, like, you know, what Harvard and MIT have done is exceptional in putting up their own courses and even a platform and, you know, sort of like giving it out. But they work within limits of accessibility. And even the programs that you showed us, which were excellent programs, you know, where you can, of course, have scholarships, you can have admission, whatever. But still, this works within a framework, which is a individual university, each one pursuing their own vision and reproduction. The European system is different. We're all publicly funded. Mm-hmm. So there is no reason on, I would say, normative grounds, even we would say on constitutional grounds, that we should not be putting forces together. You know, if you ask, but if there is a better political science degree in Padova, why you should also do a political science degree in Naples, rather than having a political science degree in Padua put online? With the best possible, I agree with you, would never be the magic, but that, you know, the magic topic is an interesting one. I mean, I am wondering what is going to happen in terms of magic with the new Apple Vision, just to make an example, you know, developments. It will never be the same. I'm not saying that, you know, having 3 students in front of you is the same thing than having 30 or 300. But still, we're only at the beginning of the big multimedia adventure. It's like Hollywood 1920s. And what is going to be in the new Hollywood of the teaching of the future. It's only to say that it will always be best to have 3 students, but if you have to cope with 30,000, why should you have 3 political science degrees or maybe 30 political science degrees, and you should have not one, the best degree that all universities put up together. In terms of the public framework of European university, this could be possible. And to me, this is an important answer because it's also, an important question, because it's the kind of question the students are raising more and more. Because, of course, for students, the possibility of accessing online top quality, I'm talking about quality because the whole problem is there. The whole problem, are you able to achieve top quality and give it to tens of thousands of students? Technically speaking, this is almost possible. I put it almost because I still believe that, of course, teaching in a classroom like this is better, but I mean, if you take the quality-quantity ratio, it's very interesting. So the answer to your question is, we've been doing a lot with Federica with respect to our means. We've been funded by European Union. We are proud of all of this. But in terms of reaching out for the kind of possibilities, which are enormous, we are just at the very beginning of this. And to me, the question is still is why German, French, Italian, Spanish universities don't pull their own resources together and do for digital inclusive education what American private universities have been better to do. So that's the political question, which of course is not for me to answer. But
I of course won't answer the question, but I will say I'm Canadian actually. I grew up in Canada, I'm a Canadian citizen, and in Canada also we have public universities. And of course in the United States, I'm at a private university. Many of the top universities are private universities, but we have great public universities in the United States also, whether it's UC Berkeley, University of Michigan, University of Washington, many. And so I think it's a really interesting question. And one of the things to point out, without answering the question, is that in both a public university and a private university, students don't pay for their education with the tuition. The cost of delivering the education that we deliver is much greater than the tuition that students pay. In a public university, say Queen's University in Canada, where I was a student, or public universities in Europe, taxpayers contribute to the cost of delivering the education, and so you can think of that as everyone pays for their education over the course of their whole life through the taxes that they pay. In a private university like MIT, where I know the numbers, undergraduate tuition is 5% of MIT's budget. Graduate tuition is 9% of MIT's budget. The overhead on research grants is about 30% of MIT's budget, so the funding for the research that we do. And more than 40% of MIT's budget, so the largest category, is either from gifts that are given by a supporter of MIT who gives a gift that is spent, or contributions to our endowment, which yields, the endowment has a return as it grows. And most of those gifts come from alumni. Not all, but most. And so in the private universities of the United States, the model is that you pay for your education late in your life. You went to MIT when you were 20, but you pay for your education when you're 70, and you give a generous gift to the university where you went 50 years earlier. And how much of a gift you give depends on what you've done between age 20 and age 70. Which is a completely different model in the political implications, the ethical implications, as opposed to you pay for your education by paying taxes. so I think there's a very, this is the beginning of a very interesting discussion that has implications that go far beyond digital learning. But I think that's the way to think about the private versus the public, is not to focus on tuition, but it's to focus on the difference between supporting education via all of society pays taxes, and then one of the things that tax money goes into is higher education. That's the public university model, versus and of course those who are most affluent pay the most taxes, versus those who are the most affluent late in their life give the biggest gifts to the university that they went to as students. I can point to negatives of both models. I can point to positives of both models, but I'm not sure I can answer the actual question you asked.
Professor Mariconda, would you like to add something? Comments or?
Yes, just a quick comment, because I think it's late.
And maybe, I don't know if there is anybody would like to pose questions to
exactly.
our guest. That's, I think we should
maybe
also.
It's better.
Yeah, that should be good.
Oh, so may I? Okay. Do you have any questions? Would you like, to share experiences or curiosity?
Yes, and there's someone with a microphone who will bring it to you.
Please, be courageous.
Hi, thank you very much for interesting talk. And I'm a university professor here in Padova, and I teach AI, but I won't ask about AI, okay? I agree with what was said here. I'm curious about the magic part, okay? This is something that I feel very strongly. And I don't think there is only a problem like with some teaching assistants that are very good and AI is not able to achieve that goal. I think there are good teachers and there are bad teachers.
Yes.
And the difference is, that the good teachers are able to create this magic and the bad teacher don't care, or they won't be able to. And I wonder if, from a scientific point of view, we could use cognitive science to explain what this magic is in teaching. Is it something with the strategy? Is something that comes out of our brain? So have you ever thought about this? Can you tell something about?
So I'm a physicist, not a computer scientist. But I will say I think a big part of this, the answer to the question, has to do with how a university is run by people like the vice rector or the rector, who is not here, by the leadership of the university, including at the department level. You have to create a faculty culture where faculty value good teaching. And you can easily mess it up. I can point to departments, I won't do examples, but when I arrived at MIT as a brand new faculty member in 1997, the physicists in the room will know some of these names, but Vicky Weisskopf was late in his life. I met him. Bob Jaffe I taught with. Barton Sweebach, whom you saw in one of the videos just ahead of me. These are just people who are really, really good teachers, and you have lunch with people who are, it just rubs off on you that part of what you do, of course we all do our research. I spoke about my research yesterday. But you have to create a culture in which good teaching is valued. Teaching awards are good, teaching evaluations are good, a teaching and learning lab, which here is Teach for Learning. These are all important, but the most important thing, I think, is the faculty-to-faculty communication of a sense of values, that this is something we're proud of. We're proud of our undergraduate education in the MIT Physics Department. And so, there are bad teachers in my department, but there's a social pressure to be a good teacher, but that it doesn't work for everyone. But anyway, I'm not sure that I've answered your question. I will say, in terms of the teaching of computer science at MIT, there are many of our large computer science classes, and we have our intro to machine learning class is more than 700 students per semester now, because it's both semesters, because a lot of master's students are taking, so a lot of undergrads take it, but then also master's students are taking it, even if they're not in computer science or math, they're taking it no matter what they're in a master's of. So we have enormous classes in computer science, and many of them have gone now to a mode where there's only 1 hour of lecture per week, and most of the week is what my colleagues in computer science call labs, which is different than what a physicist calls a lab. But in a computer science lab, I probably don't have to tell you, it's the active learning component of the computer science class. And as far as I can tell from listening to our students and listening to my advisees, many of whom take that machine learning class, they like it. They like what they're getting in those lab classrooms. Now, I don't teach computer science, so I can't go too much farther with this, but I think it would be interesting to compare notes between, I don't know, Rob Miller in MIT's computer science and AI teaching and learning effort, and someone like you here, to see how you're each responding to the challenge of I'm sure you have large numbers of students coming to your classes, as we do, trying to create the active learning experiences for students in a large computer science class is something that my colleagues have spent a lot of effort on. I didn't use examples from CS, but...
Okay, they are just telling me that we need to conclude. So, okay, so I would like to, first of all, to thank Professor Rajagopal for being here and for such a thoughtful and thought-provoking speech. I must confess that I might need to go back to my class as well. And of course, I would like to thank Professor Carlo Mariconda for sharing and for organize all this together with Professor, our Vice Rector, and Professor Marina De Rossi. And also, again, thank you very much for Professor Mauro Calise for being here. I'm sorry, maybe you can send your questions to personally. I don't know if
Well, we can continue chatting afterwards, or please send me an email, Krishna at MIT. But I want to thank both of you and Gianguido and the Scuola Galileana for inviting me. I've learned a lot earlier in the day from our conversations, and it's been a real pleasure. So thank you very much.
So again, thank you very much. See you soon. Enjoy Teaching for Learning then.